I don't know if this was true for you, but for a lot of math majors, that moment where you're sitting in linear algebra class, multiplying matrices, and you find out that if you multiply them one way, and you multiply the same matrices the other way, that you usually don't get the same answer, that moment is a big watershed moment in a math major's development. Because that's the moment at which you begin to fully appreciate that the kinds of arithmetic that you learned coming up through arithmetic and algebra in high school, there's something special about it that made multiplication of integers or rational numbers or real numbers, it made those multiplications commutative. But that matrices, even as seemingly straightforward as they are, just arrays of numbers that have a particular way of defining how to multiply them, they're of course more than that, but at the time that's probably what they were for you, that there's something about their matrix multiplication that didn't permit for that commutative property to hold. So in abstract algebra, what we want to do is again ask those questions. What kinds of algebra can we still do, even if the commutative property, which held in this very important special case that you learned when you were coming up through middle and elementary and high school, what kinds of algebra can we do where that property doesn't hold? We know by definition that the operation in any group is associative, satisfies the closure property, the identity property, and the inverses property. But the commutative property is not on that list for all groups. And I would say that most groups that we'll meet out in the wild don't have that commutative property. So in this couple of videos, what we want to do is look more closely at the commutative property. What can we do when we can say that the whole group enjoys that property, in which case we will call that group an abelian group. And then afterwards, we want to start to take in groups that are not abelian and focus in on places where the commutative property does hold, maybe on a smaller scale. So we'll be able to ask questions like, okay, if everything in the group, if all the elements don't satisfy commutativity, then maybe some of them do. And those that do, we will call the center of the group. And then lastly, if you hand me an element, how do I talk about those things that it commutes with? So answer the question, for a given element, what commutes with me? And that's answered by something called the centralizer. So commutativity, abelian groups, the center of a group, and the centralizer of an element are what we're about to talk about. So first things first, as I mentioned, if we have a group, all of which satisfies the commutative property, so every pair of elements, we can reverse the order of the operation and get the same result, then that group is called an abelian group. So abelian groups, named after the mathematician Abel, sometimes this A is capitalized for that reason, but I think it's a pretty high honor for somebody that you name something so clearly after them, and in a lot of places it ends up being an improper noun, just a small letter A. So we say that a group is abelian if that operation is commutative, if GH is equal to HG for all elements G and H in the group. So when this happens, we'll usually colloquially say G commutes with H. So to say that something commutes with something else means that I can reverse the order in which the operation is applied to them and get the same result. And again, to say that a group is abelian means that every pair of elements in our group has to commute with one another. So what's an example? Well, how about one of the modular arithmetic groups that we've already been working with? So for example, the additive group of integer residues modulo 5. This is an abelian group. And the way to see that is just to take a couple of equivalence classes mod 5, just pick them arbitrarily. I'm pointing out that they're arbitrary here because I'm going to satisfy a universal claim here for all. And if I add these two things together mod 5, if I add their equivalence classes, then by construction of how we got these equivalence classes, I can also add the integers first and then take the equivalence class, mod 5. We can show that that's a well-defined operation. In fact, this is one way to define what addition mod 5 looks like. Just add the integers and then take the remainder when you divide it by 5. But what do we know about the addition of integers? Addition of integers is commutative. And so because the addition operation on integers is a commutative operation, we can trade places with x and y and make them y plus x, because we know, or we can take for granted at least in this course, that the addition of integers has the commutative property. And then again, by construction of equivalence classes mod 5, we can also split this apart into the sum, mod 5, of the equivalence class of y and the equivalence class of x. So when we read this from beginning to end, for all elements in my group, Z mod 5, that I can pick, we find that the sum is equal if I do it one way versus if I do it the other way. So the additive group of integers, mod 5, is an abelian group. And so, in that case, every pair of elements in my group commutes with one another. But if I have a group in which that's not satisfied, for example, the group of rational tangles, or the group of symmetries, the dihedral group of a polygon, or a group of permutations, or there's a whole lot of groups that we're going to meet in group theory that are not abelian groups. And yet we'd still like to be able to occasionally make use of the commutative property. And we can do that by focusing in on a subset of elements and ask, if all of them don't commute with one another, what if just some of them do? More specifically, what we'll do is ask, what is the subset of elements that commute with everything in the group? So what are the most easygoing elements in my group as it relates to the commutative property? Now, first of all, we always know that that set is going to be non-empty. Why? Because every group has at least one element that does commute with everything. Namely, that's the identity element. Because the identity property is a two-sided identity property, right? That for any element G in my group, identity times G is equal to G times identity, because both of those are equal to G itself. Again, that's the identity property. So if we ask the question, what is the subset of elements in my group that commute with everything in the group, that subset will always at least have the identity element in it. It may also have other things. If the group is abelian, in which case everything commutes with everything, then this subset of elements that commute with everything turns out to be the whole group. But there are also examples of groups in which the identity element is the only thing that commutes with everything. And every other element in the group, we can find at least one example of a commutative relation that does not actually hold the way that we would like it to. So this subset of elements that we're about to call the center of a group, it can be the whole group, in which case the group is an abelian group. Or it can go all the way down to be as small as a single element, the identity element. And it can be everything in between. Well, not necessarily everything, as we're about to see. So here's the definition. The center of a group is the set of all elements in that group that commute with everything. This is the set of easygoing elements that the commutative property will always be okay if one of these elements is part of that expression. So xg and gx are going to equal one another when x is an element of this center. And that's true for all elements G. We denote the center of a group G by ZG, Z being the first letter in the German word for center, which I don't remember off the top of my head. So the set of elements that commute with everything. And as I was just saying, if our whole group is abelian, right, if G is an abelian group, that means that every element commutes with everything. And so in the case where G is abelian, the center of G is equal to all of G, and vice versa. So, okay, what can we say then about the subset of elements that commute with everything? What's true about the center of a group? Well, I've been calling it a subset up until this point. But in fact, more is true, and we're about to prove it. That any group whatsoever, doesn't matter if it's a finite group, an infinite group, anything, for any group, the center of the group is a subgroup of G. It's better than a subset. It's actually a subgroup. And we're going to study subgroups a lot this semester. We're going to see very quickly that subgroups of a group are very tightly constrained. Not every subset of a group turns out to be a subgroup. And so this means that if I know what the subgroups of G are, one of those subgroups has got to be the center of my group. So let's write a proof of this. Remember that proving something is a subgroup, if we go back to the definition of subgroup, would mean that I have to show that the center is a group in its own right. I have to show that it meets the associativity property, the closure property, the identity property, and the inverses property. But I don't think that I want to do all of those things separately. That's a bit brute force for me. And in our previous video, we talked about a theorem called the Subgroup Tests theorem that gave us 3 criteria, any one of which is equivalent to the statement that H is a subgroup of G. And they're a little bit easier to check. That's why we call them tests. Rather than going back to the definition of subgroup, if we can check one of these 3 criteria and show that it's true, then that will imply that our subset is a subgroup. So we're going to use a subgroup test. Rather than verifying all 4 of those properties, we're going to try one of those tests. I experimented a little bit on the back of a piece of paper, trying out these different subgroup tests for this proof. I decided to settle on subgroup test number 2. And subgroup test number 2 has us verifying 2 things. It's called the 2-step test. The first is we need to verify that for every element in my subset, its inverse, and it has an inverse because it was an element of G, its inverse as an element of G is also an element of my subset. So that's the first thing I have to verify. And the second thing I have to verify is the closure property. That for 2 elements of my subset, the operation, if I operate on the 2 of them with the operation of the group G, that their product is also still inside of my subset. If I verify just inverses and just closure, then the subgroup test also guarantees associativity and the identity property. And so these 2 things are all that I have to verify invoking subgroup test number 2. So let's do it. Unpacking the definition of, for my first implication here, if I want to prove that for every x in the center, its inverse is also in the center, remember that x being in the center, by definition, means that x commutes with everything in the group. So xg is equal to gx for any g from the group that I put next to my x. If I assume that to be true, setting myself up for a direct proof, then my burden of proof would be to show that x inverse also commutes with everything. And so I'll take that burden of proof and write it down. What would I have to do? I would have to show that for any g in my group, x inverse g equals gx inverse. How am I going to prove that, knowing so little about the group that I'm working in? Right? I don't know anything about this group. The only thing I know about this group is that it's a group. And so I have associativity, I have identity, inverses, closure, and those imply the various other group properties that we've studied, but we don't know this is an abelian group. It's probably not an abelian group, but this is going to be an interesting question. And so there's a very limited number of things that I can do to manipulate this expression and turn it into that one. In particular, as I'm looking at this proof with a little bit of foresight, I'm going to say, well, if I squint real hard, what I'm really trying to do is leapfrog this x inverse so that it's on the other side of my g. So I need some tool to be able to reverse the order of 2 elements in an operation without knowing that the commutative property is true. Let's assume the commutative property is not true in general, right? Because otherwise we'd be begging the question. Right? Begging the question would be something like assuming that x inverse commuted with something. We can't do that. We have to prove that this is true. Now there's one property that's true in every group, anywhere, ever, whether that group is abelian, whether it's not abelian, whether it's a finite group, whether it's not a finite group. Every group has one thing that allows us to change orders of multiplication of elements. It's the shoes and socks property. If I can cleverly use the shoes and socks property, then I'll be able to leapfrog the x to the other side of the g at the cost of introducing some inverses into my mix here. So I'll do that. Remember, the shoes and socks property says that the inverse of a product is the product of the inverses in the opposite order. So if I can write this product as an inverse, then it's the inverse of a product where the g thing and the x thing appear in the opposite order. And looking at it, if the g comes second in this product, it will come first with an inverse in this product, according to shoes and socks. And if x inverse came first over here, it comes second in my shoes and socks, except that it appears as its inverse. And x inverse inverse is x, because of the uniqueness of inverses property that holds again in any group. So now 2 things are great. First of all, I've got the x on the other side of my g, as I wanted, because I'm trying to get to this expression. And it's no longer an x inverse, which I don't know anything about. Now it's an x, which I do know something about. I've assumed that x is an element of my center. Therefore, it commutes with everything. In particular, it commutes with the element g inverse that it's sitting next to inside of my shoes over here. So that means that by assumption, this x can multiply this g inverse on the other side without changing the expression. G inverse x is equal to xg inverse. Why? Because g inverse is one of the elements in my group, and x belongs to my center by assumption. Once I've traded those places, then applying shoes and socks one more time says that the inverse of this product is the product of the inverses in the opposite order, which means that the first thing I'm going to get is the inverse of g inverse, that's g. The second thing I'm going to get is the inverse of x, that's x inverse. And so shoes and socks gets me right to exactly where I wanted to go. Reading that from beginning to end, we can see x inverse g is equal to gx inverse. This was true for arbitrary g, and so x inverse belongs to the center. All we had to do is take off our shoes and socks twice, right, and apply the assumption we made about x. I think that was the tricky part. Let's see what happens if we try to prove the closure property. Again, directly, assuming that x and y belong to the center, so x and y commute with every element in my group. How do I know that their product xy will commute with every element in the group? So I need to show that xy times g is equal to g times xy for any element that I could pick, any element g from my group that I could pick. So how am I going to do that? Well, here it's not shoes and socks that's going to bail us out. It's the associativity property that allows me to take the parentheses around my xy and nudge them to the right so that they're surrounding y and g instead. And then use the assumption that y belongs to the center, right? We assume that back here, which means y commutes with every element of the group g. So in particular, y will commute with little g, which means yg is equal to gy. Now I've leapfrogged my g one step. I've leapfrogged it over the y. Now it's next to the x. But what do we know about x? X also is an element of the center, which means I can leapfrog the g past the x as well. xg is equal to gx. And applying the associativity property one more time, we get exactly to where we wanted to go. G times the quantity, xy. Alright, so now I've done all my work on the back of the bar napkin over here on the left side of this line. Let's turn this into a proof to wrap up this video. I wouldn't hand this scratch work here into an academic journal for publication, so let's write up something that we would be proud to be a way to actually communicate the logic that I just talked through with you over the past 5 or 6 minutes in written form. So we'll start the proof by indicating to the reader what the overall strategy of my proof is going to be. We're going to use the two-step subgroup test. So we're making an appeal to a theorem that we proved in the previous video, and saying, if I can show that the assumptions of this subgroup test are satisfied, then by that theorem I will have proven that ZG is a subgroup. And so then I'll write down the 2 steps. Step 1, I need to show that the inverses property holds for my subset ZG. For all x in ZG, x inverse belongs to ZG. Because this is a for all statement, I'll start by picking up an element of my center arbitrarily. So let x be an element of my center arbitrarily chosen. I don't get to construct it, I just have to deal with whatever element from the center that the universe wants to hand me. So let this be arbitrarily chosen. And then I go to the step that we did over here, where we reminded ourselves what it means that x belongs to the center. So we translate that definition into something actionable. By definition of the center, we know that for all elements of my group G, xg is going to equal gx. So all we did is plug in our definition of the center of a group. So now we have to show that this holds for all g and g. So my new burden of proof is the second half of this sentence. For all g and g, we have to show xg is equal to gx. And looking toward what the end of our argument on this first step is going to be, we need to show that x inverse belongs to the center of g. And if x inverse belongs to the center of g, applying again the definition of center, we have to show for all g in g that x inverse g is equal to gx inverse. So we know this statement. We want to prove this statement. So we're assuming this light blue thing. We want to prove this purple thing. Each one of them is a universal statement. For all, for all. But the universal statement that we wish to prove is what gives us the next line of our proof. What we need to say is, let's again make an arbitrary choice. We have to prove that for all g, x inverse g is equal to gx inverse. So let's let the universe arbitrarily choose a g for us. Then, in order to substantiate this claim, that's where our shoes and socks argument comes in. Then, x inverse g is equal to g inverse x, the quantity inverse. Now, by definition of the center, because x belongs to the center, and g inverse is an element of the group, we know xg inverse is equal to g inverse x. So I can replace g inverse x with xg inverse, apply the shoes and socks property one more time, and I've proven exactly what I set out to prove in step 1, that x inverse g is indeed equal to gx inverse. That concludes step 1 in my two-step test. Step 2 is the closure step. We need to show that for all x and y in the center of my group, xy is also in the center. Again, because this is a universal claim, we're going to start this step in the proof by saying, let's let the universe arbitrarily choose an x and a y from the center of G. Which means that for all elements G in my group, x and y both commute with G. So xg is equal to gx, yg is equal to gy. Now what I want to prove, so writing the last line of my proof here, I want to prove that xy is in the center. Which means, by definition again of center, we need to prove that xy times g is equal to g times xy, and that this holds for all g in my group. So because my burden of proof is universal, I have to start out by letting the universe pick my g. Let g be arbitrarily chosen, and then we deploy our argument. xyg is equal to x times the quantity yg, which by assumption, because y belongs to the center, is equal to x times gy, which by assumption, because x belongs to the center, is equal to g times x times y. And therefore we've shown that xyg is equal to gxy, proving that xy belongs to the center of my group. So this was kind of a long story in this video, a little bit longer than my usual, because we started out with this pie in the sky idea, that when the operation in a group is always commutative for every pair of elements, we call that group abelian. And we like these groups a lot. It turns out that even abelian groups have a lot of interesting things we can say about them, but having that commutative property that we can take for granted is really nice when it comes to actually making calculations and solving equations. But when groups don't have that property for all of their elements, they will always at least have it for one of their elements, namely the identity, and possibly many more. And that subset of elements which do commute with everything in the group is called the center of that group, ZG. And as we just proved using a two-step subgroup test theorem, we proved that not only is the subset of elements that commute with everything in the group a subset, it turns out that it's a subgroup as well. And so the center of a group is always a subgroup, as we've just proven.